Welcome to this lesson, friends. In this one, we're going to take a look at the following questions. Examples of one-sided limits for specific functions. Let's begin with this function. F of x is defined here as the square root, say, of 2 minus x. I want to take a limit on this. First of all, how should the limit be taken? Let's just review the concept of domain. So for a square root function, 2 minus x should be greater than or equal to 0. So for this to be true, we should have that negative x is greater than or equal to negative 2, that divided by negative 1, remembering to flip the direction of the inequality, so x is less than or equal to positive 2. That's the domain. In other words, any value of x to the left of 2 could be 1.99, it could be 1.99999, and so on, as long as it's to the left of 2 or equal to 2. Because there's a possibility that it could be equal to 2, I could form this limit. The limit, as x approaches here 2, and because it's x less than or equal to 2, the limit has to be taken from the left side of 2. So up there, put a little negative. And the square root here of 2 minus x, and this one can be done through direct substitution. So it's going to be the square root of 2. You can directly replace x with 2, and that's going to give you here the square root of 0, which is then just 0. And that's the value of the limit. Look at the next one in the process here. Imagine we're given here h of x, and this is now 1 over square root of x minus 2. This one is different compared to the last one. First of all, because this time you have division in a square root operation, you cannot divide by 0, remember, and the value under the square root has to be then also positive. So you have to incorporate both. You can do that by typing the following here. X minus 2 is greater than 0. So notice that this one is different. It has to be greater than 0 strictly. There's no possibility of being equal to 0 because that would lead to division by 0. Then here I'm going to have the following. X is just greater than 2. Simple enough. The question then is, where is there a limit in here? Well, what are values of x greater than 2? Think about it. 2.001 or 2.00001. Those values are greater than 2, but they're to the right of the 2. Greater than 2, to the right of the 2, but very, very close to 2. In other words, what this is suggesting is that we should take the following limit. The limit as x approaches 2 from the right side of h of x. That's our goal here. How do we answer this question? Well, it may not be so obvious as the last one, and you cannot plug 2 in because that would lead to division by 0. So when you have that situation, try to plug in values and see what happens in terms of a pattern that emerges. So I'll do example 1 over square root of 2.0001 minus 2. Calculate this quantity. So when we do that here, we end up with 100 as the output. So it's getting pretty big and positive already. So 100 is a good approximation. And let's do it one more time. 1 over the square root of 2.0001 minus 2. And that's going to give us a value then of 316. I hope you can see by now that the values are getting bigger and bigger and bigger and bigger in terms of the output for every input, which suggests that essentially the limit as x approaches here 2 from the right side of h of x is basically infinity. You can confirm this with a graph, but I'm deliberately skipping graphs in this one. The graph is not always available, and it takes time, so you can also be able to reason through these questions without graphs. One last example. F of x is defined as the following. 2x plus 4, and we're going to use this when 0 is less than x, which is less than or equal to positive 1, and then x squared, say when x is less than or equal to 0. Where can I take a limit in this kind of function? By looking at this, maybe you can tell that an interesting place to take a limit would be around 0 itself. So imagine I said, take the limit here as x approaches 0 from the right side of f of x. The question is, which piece should be used in the limit? That may not be obvious when you have a piecewise defined function. So then you have to understand that x is approaching 0 from the right side. What is such a value of x then? An x value could be the following, 0.00001. So in other words, it's a value, it's to the right of 0, but it's very close to 0. That value fits within this interval. 0 is less than 0.00001, which is less than or equal to positive 1. It makes this top inequality true. Why do you want to see that? Because it tells you then 2x plus 4 is the expression to be used when you take the limit. And then here we can have the following. The limit as x approaches here 0 from the right side. Basically 2x plus 4, and again that can then be done through direct substitution. You have 2 times 0 plus 4, which is equal to 4. That's the value of the limit. You might also answer this question, the limit as x approaches here is 0. And let's say from the left side of f of x, which piece do you use? Well, to approach 0 from the left side means to approach 0 through negative values. So which one would it be then? The top or the bottom? It would be the bottom piece, because that's the one that has x less than or equal to 0. When you're approaching from the left side, you're approaching through values less than 0 until you get to 0 itself. So then you could do this with direct substitution essentially. This way, limit as x approaches here is 0 from the left side of x squared. And then you can also do this with direct substitution, so it becomes 0 squared, which is then just equal to 0. You can confirm these calculations very easily for each example, simply by graphing the function, observing what happens in the graphs. But that is it. So thank you, friends. I'll see you in the next lesson.